Welcome to today's webinar. The topic today is form finding and calculation of membrane structures in Rfem 6. My name is Andreas Hörold. I am responsible for marketing and public relations in the Dlubal Software company. I will be the moderator today and I will answer your questions together with Stefan Hoffmann, but my two colleagues can introduce themselves.
Hello, my name is Andreas Niemeyer and I'm responsible for the product engineering here by Dlubal, and today I will present you this webinar.
Okay, hello, my name is Stefan Hoffmann and I'm working in the customer support, and I'm also responsible for dynamic analysis, form finding and wind simulation. And today I will answer your questions within the chat.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can enter a short question here and we will answer you. In the case there are too many questions in the webinar and you don't get an answer, you will get an answer after the webinar via email. The other way is to watch the entire webinar and email your questions to info@dlubal.com. Okay, then I hand over the screen to Andreas Niemeyer.
Thank you, Andreas. Then I overtake with the topic form finding and calculation of membrane structures in Rfem 6 today. Here So I selected today a special example which inspired me in our last exhibition trip in Cologne. We traveled here from the central station to the exhibition area, and I always saw here this musical dome structure, and I selected this for the today's webinar. This structure is a special membrane structure. It's an arc-supported membrane roof. Where I want to show you how you can model such type of structures in Rfem, and because this structure is gives you a special shape what is not covered from the typical wind standards, I will show you how you can generate with our digital wind tunnel wind loads for this structure. And because this membrane will produce given pressure in the members, I will take a look on the stability behavior of this model, and finally we sum it up with a design of the members and the surface parts. To get also a picture how it looks like in reality, I found a picture on the Wikipedia page. Here is this musical dome, and for imagination, this is the real life example what we want to model. If you see it here, this membrane is supported from two pairs of arc, one lower arc and one higher supported arc. And this roof covers, let's say, a massive building block. And this is the keyword for our modeling start, where we change to Rfem and try to model it in a live demo here. For this, we give a name, maybe PO5, and decide which tasks we want to do here. As mentioned, we want to take a look on the stability behavior. Therefore, I activate here the structure stability add-on. We have to find the right place of the membrane roof. Therefore, I activate the form finding add-on. We have to generate wind loads. I activate the wind simulation. And to sum it up, we want to do a steel design for the members and a stress design for the membranes. Because we selected here a steel design and we have to work with design itself, we will be forced in the third register to define the standards itself. As mentioned, this structure is created in Cologne in Germany. Therefore, I select here from the Eurocode 0, the German annex. The same for the load wizards, because we have to generate the wind speed diagram over the high, And for the steel design, I also select the DIN annex. And this brings me to the confirmation. I say yes here and open an empty model with all these properties, and will be able to start. During introduction, I mentioned that the membrane roof covers such a block building below. I produce me a technical drawing which gives me these building properties itself. So I use here in our program the background layers. You will find it here below guide objects as last item, and you can open here a background layer, a new one, and can maybe give here a name, for example here base geometry, and select any file you want to import here. I select here this building shape, and you see this is this building or massive building block we want to cover with our membrane roof. The only thing what you can or have to define is at least the, let's say, the scaling of the unit. My technical drawing is based on meters, therefore I have to select it here, and the other settings will allow you to rotate or mirror and so on. So with confirmation of this item, we get such a line geometry in our Rfem, which gives us these basic geometries for our roof. If you pick on this element, you could assume it's lines, but it isn't. It's only the geometry you imported, but it don't produce us some line elements itself. We have to, let's say, use these points to create it, but it will not create that stuff automatically. So I start by describing our program the edge of roof on top. I define here such a line res around. By picking this, let's say, crossing nodes, and this produced me finally a few lines in the basic objects. Now you see we have some lines. Now let's take this geometry as start condition, but as you saw also on the pictures, the roof is covering this building block a little bit. Therefore, we scale it up that our roof really covers this block. And let's take some measurement, for example, 0.5 meter. I copy this node here with copy and use here, for example, 1.5 and produce me here such an control node which should be almost covered from the roof. And for the scaling, I create here a center of scale. Therefore, I pick here such a center, and now we can take this basic geometry, we select it with a window and open or start this command scale. Define we want to copy it, and the, let's say, base point of this operation is this point in the middle, what we just created, and the scaling factor we pick here directly by defining the original length and the target length. And with confirmation, we get now our really or our final expected edge of membranes on the eave, and this is now our basis for the further modeling of this roof. Now we know where the roof is starting on the eave, and in the next instance we have to think about how we generate these arcs, this pair of arcs in this structure. And I would say let's start with the foundation. So use the lower side of the wall, pick again here a line into the system and take the dimensions of, let's say, the architectural concept. And here we know that these arcs have the outer distance of the arcs is 41 meters. If I check this line here with the tooltip, we see it's almost 50 meters. So we have to shorten it, but before we will move it on the right place where the arcs will start on the bottom. So we go to the move command, deactivate this option, and move this line here with 6 meters in y direction. So now we're knowing that the arcs will start at this place around, but the outer dimension is 41 meter. So we select this line and use here the option extend line, where we can say, please give the line a new length with 41 meters on both sides. You can modify, and with confirmation, now we get a line with the length of 41 meters. Now we have to divide it to get, let's say, the starting points of the inner arcs. Here I select the line and use the distance division, where we define here maybe the first distance is 15 meters, apply, and the second is also 15 meters but measured from the right side, so right here 15. So this gives us now 4 nodes. And these 4 nodes represents, let's say, the foundation of these supporting arcs. Because the arc starts on one end and ends on the other side, therefore we mirror it on the right side with the mirror plane XC, and the mirror point is in the middle, so everything is fine, and we get it on the right side. So then we can starting modeling these arcs. For this, you have to know if we take a view in X direction, that this arc should start here, should touch our, let's say, boundary line of the roof on this eave, should run above and should touch it here again and end here. For this, we need, let's say, the intersection point from this plane here, or maybe from this point here. And how to get this? For this, I recommend to use our working plane, so this dotted plane, and we will move the center of this plane, for example, to one foundation point. Now we rotate this plane into this intersection or in the plane of the arc, and will be able to create intersections here. For this, I use a surface. The stiffness of the surface is now irrelevant because we need it only for finding a right geometry. So I define here without thickness and select this plane. Then we can create an intersection node between this plane and this line by using this connect function and drawing a window about. Now we get this node. The same on the another side. And we get also here this node. Now we have all this information and we can delete this surface because it's not needed anymore. And we can start creating this arc. For this, we use here a line with the function arc, where we pick the foundation node, the eave, and the foundation node on the other side. And you see, if we take a view in X, that this arc will be divided directly in 3 parts and touches exactly this node here, what was expected. In the next point, or if you remember when I showed you in the introduction the pictures, we have also to deal with with a different arc level. So this is the smaller one, and we have also to create one what is, for example, 5 meters higher. And with seeing this, we have to go away from this circle definition. We need something more general. So here I recommend to work with splines. And to work with splines, we need some control points. And for this, I take this upper arc part and divide it in, let's say, parts, for example, in 5 elements here. And now we can, let's say, delete the lines in this part or in this plane and get only these definition nodes, these control nodes. Delete. These grid points we can hide. And we have now some nodes which we can use for spline definition. Because we need this, let's say, control nodes for the other arc also, I copy directly this basis on the another side and create directly here this, let's say, geometry with this lifted arc. For this, I need a center in between. I use this command node between 2 other elements here, apply. And now I say, okay, this left arc should, for example, lift it with this 5 meters. I copy this top node, create copy with -5 meters upwards. So if we take a look in this view, you see, okay, we have to move these control nodes up to this top level. And now to think how we can do this. Of course, we can scale it, but if we scale it, this node will be not only moved in this direction, and also moved in the, let's say, radial direction. Therefore, I want to recommend here a special scale command, which you can use like this. You select this node set. Open here, edit, go to scale also. Create copy is not needed, but you see, if you scale something, it will not only be moved in scale directions and also in all other sides. But here is additional function hidden, a 2-point scaling, where you can let the size of the element similar, but you scale it only in one direction. And for this, we define here the scale direction from the center node to top, and the scale factor from this, let's say, center node. This is origin length, and this will be target length. And with confirmation, we can move these nodes a little bit upwards. And if you take a look, you see the program moved it only in this direction I defined. And now it's ready to bring in these splines. So the lower arc at first. So we start on this foundation on Eve, then on these intermediate nodes, and we can draw really easy this arc or spline above. The same we can do for the bigger arc. And here, yes. Now let's check this data. And you see we get 2 arcs. They are almost homogeneous, but of course we have here not a covering, what is clear, because we have to deal with different geometries, but it's giving us a homogeneous shape for supporting this roof. And now we have to, let's say, to modify it. Because if we take a look in this view, this architectural concept of this roof forces us that we rotate or incline these arcs a little bit into right side and this one into left side. Let's assume, for example, 20 degrees. And further, there is a requirement that this top level remains. So when I rotate this arc into right side, it would happen that it's going down on the way of a circle or arc. But this level should remain, and the same here. And for this option, our program offers a camper function, and here we select the full arc, go to Edit, use camper, and say here, for example, -20 for the right one, and rotate around y-axis, and move the nodes into only in x direction around this foundation node. And with confirmation, the arc will be moved, but all these nodes remains on its level. So, and the same we can do for the other side. We go to Edit, Camphor. Now we have to change the direction, and to change this rotation part, and with confirmation, it will be moved in this direction. And this is now the state where we can say, okay, nice, the arcs, we have defined this definition of these arcs, and it's ready to copy. Yeah, so we can copy this geometry and copy it on the right place, and the same, so the higher one, select it and copy it on the left side. So far, we have now almost all boundaries for this membrane. The only point what is not so nice is now that this, let's say, Eve point don't cut exactly this corner of our, let's say, safety place that the membrane covers the building itself. I will correct these situations by moving this node a little bit, because it's not crucial if we say, okay, the roof should be connected to this corner here. So, and here's the last one. And now, let's say we have all geometries here to envelope our roof shape. For this roof shape, we will introduce now surfaces. And for these surfaces, we offer here planes and, let's say, curved. Of course, we have to deal here with curved, and I use here quadrangular surfaces. I define here the stiffness type membrane with a specific thickness type, what represents a section of, or a cross section of a surface. And here I open the library and select here the category fabric, and you see we offer here PS, PWC values, or class PTFE, or also ETFE values for the starting of such an analysis. It's clear that these values should be checked for the real project, but it's a mean of everything what exists on market. And we take here, for example, this type 4 and confirm it, and the program automatically define here this reference thickness for the stiffness values behind, and now allows us to pick the boundary lines. Let's start from left side, then specify here maybe this arc part, this middle part. I only select the boundary lines if the program finds a unique way of line. It will select the part directly and will finish the surface input, and now maybe the end cap on the right side. So far, it looks now almost like a roof, but you see here directly you have sharp corners. It's only a representation of the picked boundary lines. Here is no form finding condition or something else now considered. If you want to do form finding, you have to give the program the information for which or force state it should find a good place of finite elements in space. And let's start with this condition elements. For this, let's mesh this surface directly and take a look on this initially mesh, what should be optimized. And if we take here a look on wireframe model, we see, okay, mesh on top view is homogeneous, but on this end caps, it don't look really nice. And this situation comes up because this quadrangular surface is made for surfaces with 4 lines, and if you use more than 4 lines, it's a mixture of everything, and you have to define these quadrangular points more in detail. And you can do this in the surface properties, and you should specify these nodes like they span up something symmetrical, rectangle or quadratic surface. And with confirmation, we can give this information. Now we see it's more symmetrical placed. We do the same on the another side. So here also define a more symmetric place of these elements or shape conditions, and store it. Now if we remesh it, you will see this have a really ruling effect. Now the mesh is more symmetrical, more suitable for this structure. And this is now the state where we can think about how we can move these elements in space to get a good shape. For this, we have to bring in some boundary conditions. Let's say the first boundary condition is the support. Let's select here the surfaces with, for example, the membrane material, and display here also the connected elements. And now we are able to distribute on these lines, for example, a hinged support. Now, this is the first boundary condition, and the second boundary condition is a force definition, which force should be held from the surface. And for this, we need a load case. Here, I open a new, or I modify existing load case. In this case, the first one, we define here pre-stress with the action category pre-stress. The name here is irrelevant. The only important fact is this yellow flag here, because this flag gives the program the task to make a form finding process. Now let's define forces for this form finding process. In my situation, I deactivate the self-weight and apply on the surfaces itself a pre-stress by using this form finding load type. Here you can define if you want to, which concept you want to use for this type of surface or shape. A standard method is acceptable, and form finding definition could be done by force or stress. We use force with 1 and 1 kilonewton in X and Y or warp and weft direction. Now place these forces on the structure and we get a symbol of it, and now we can run our first form finding task and say, please program, find a good place of all finite elements to cover or to hold this pre-stress what we defined between these supported lines. And if you take a look now on the results, you will see that the program modified the shape of the surfaces a little bit. You see we have here a sag in all directions and even here in this direction, and this colored gradient shows us the let's say this deflection from the origin place to the new place. So far is everything nice. Even the surface holds the forces what we have defined here. For example, you see we are almost by 1, and even in the other direction it's almost 1. But the only unnice thing is that we have here a really big sag, and I want to lift it a little bit that we don't have here such a big sag. And to reduce this sag, we have to, let's say, to reduce this tangential pre-stress direction. For this, we should change one figure here, but I don't know what is y and x at the moment. We have to specify it. And for this, let's delete mesh to delete results, and maybe draw a direction in space to control the directions of the elements. So I use my working plane again, do it here in the XY plane, and draw in the middle a line from here to here, and this line should show me the span direction between the arcs. I will say it's X, for example. Therefore, I select all surfaces, going to the properties, and define here a specific axis direction with the input axis. And here I can define axis parallel to lines, and say, okay, x-axis is parallel to this line what we just draw here. And now I know, okay, x is running between arcs horizontally, and if I open the pre-stress here, I can reduce, for example, the tangential direction to 0.5. And if he runs this again, we will, or we hope we get another shape. Let's see, it's converging, it's an iterative process, of course. And you see now the sag is not so deep. And if we take a look on forces, you see, okay, this X pre-stress is again almost by 1, what is defined, and the tangential pre-stress, you see directly a color difference. It's here for left and right part by 1, and for the middle part by 1.5 or 0.5. So now I would say the shape itself fits, and we should start thinking about how we can connect it to these arcs, what we really defined quite exhausting. And these arcs have to overtake, let's say, the resulting forces what the membrane brings in here. And let's take a look what force is coming here. Let's take a look on support forces. Maybe to get a better overview, I hide mesh. I hide, for example, these support symbols, type for lines, and let's take a look on components. Maybe at first this vertical component, and you see, okay, maybe to hold equilibrium, this support have to overtake these vertical forces, even this eave around, and it have also to support this horizontal part of forces. And this force should now overtake them from such curved trusses, and yeah, let's model it. For this, we can, let's say, remove the support on these lines. Yeah, so go here to line, edit, and remove the support. So this is the first task. Now it's open, and now we can say, for these curved lines, so let's select it, curved lines, it's the NURBS geometry after spline import. We can select all and go into the properties and connect to this line geometry a member. We connect here a beam type which can overtake all forces with a section. Let's go to library, use such a scalable circular hollow section, where we say, okay, it should be from steel, so material type steel, S355, from Eurocode solution, for example. And the size of this circular hollow section, because it's pretty big, let's take 1 meter by 25 millimeters. So now, after using this or confirming this dialog, you will see that the program add into this graphics these beams. It's now not only graphics, and even the stiffness terms are added here, and the membrane connects to it. But if you watch this, this will not be stable because the beams are not linked and have no bracings. So let's start with the linking, so producing truss beams here in between these division nodes. But when we take here a closer look, you will see that we will get here or run into an issue because the membrane edge is exactly on the place where this linking beam should come. So for this issue, for solving this issue, we have to produce a situation that you can have here a straight line between these two definition nodes, and later that we can connect the cable here on another place. And for this, we select this line and say, please be an arc. And the SEC should, for example, run into inner side, and this is the dimension itself is now not interesting because form finding will search the right place. It's only that we can produce more mesh nodes at this situation, and we have to do this for all situations. So we use here also arc again here as center, and change here to 5, and now also on these lines, type arc, control or sec node, and change here this value to any another value. And now the last one, go here to arc and pick here this node and change this dimension. So now this edge of membrane is moved a little bit, what gives us the option to draw a line or a member in between. And for this, I open the new member option, use here member type truss because it's hinged on both sides, and open a new cross section. And for this, we use again this steel material with a diameter of 250 by 8 millimeters. So, and now we have to be concentrated to pick all these nodes, and let's place these linking members in between. Here between these blue division members, the same here. And now I made an error, you see. Let's correct it afterwards. And also here. And here on the eve left side, now do the same on the right side. And now you see if you found the right node, if the I made an error. If the program symbolize it with such an yellow symbol or snapping point symbol. And now the last one, and then let's correct this stuff what we made wrong. So move this node to this situation, and here was also an error, move this node to this situation. So if we take a look in isometric view, you see so far it looks fine, I hope. Now we can start adding a bracing. And again, at first select here the member type. It's in this case a tangent member, what can only overtake positive normal axis forces from cross section, because it can only overtake, or because it can get only tangent. I can use a small or a cross section what is have no big bending stiffness. So I use here a circular massive section, maybe for example with 28 millimeters from this steel, and now pick these bracings into these cells. Now this is the top ridge, and again here downwards, and now here's this eve point and foundation point. Now the same on the right side. And now the last sequence from here to here to here and foundation. So now you saw I did only a half of it. Of course, please see it always like this. If you can mirror something, mirror it. It helps to save errors. For selecting all these members, I use the cross-section table, for example. Select here or set my focus to this cross-section. You see this get highlighted, and I can mirror it by creating copy with XZ plane, and with OK, we have it also on the other sides. So this is almost done now. The membrane is supported, and we removed even these line supports on the arcs, but of course these curved truss girders have to transport the force down to the foundation, and we need here a nodal support on the bottom to overtake these forces. And now it's ready, and we can start calculation. And now we can see the effect, what happens when we hang in the membrane with this arc support, and these arcs will overtake these forces from the membrane and transport it down to the bottom. So for you it's easy, because this boundary line of membrane should be the boundary line of member, and then you can connect it. And what happens now? Let's take a look at first on the shape. So the program still have the shape what we detected or defined with the rigid solution, but now the force of the membrane will be transported to the curved truss girders and will be transported mainly with normal axis forces down to the bottom, where you get support forces on these arcs. So I would say not so complex. And it brings us to the last stage of this model creation, to think about this rigid boundary of this membrane on the eave. And if we take here a look on this structure or part, you will see, maybe make a top view without results, maybe hiding the rest. You see, okay, this green supported parts is the boundary of the membrane, and we can replace it by cables. For this, let's select only supported lines. So this is this part, and now we can select all these lines or boundaries of membranes, go into the properties, and add a member. And in this case, no beam or something with bending stiffness on. Let's add a cable. And of course, we need some suitable cable section. So go into the library, maybe to the solid sections, shape. We can take here cables. Let's use one, for example, this with 20 or 21 millimeters. And let's add a cable, a suitable cable material like this. So, and yeah, with confirmation, the program is giving this cable stiffness on these lines. What is working so far? but we in this stage, of course, we have also to reduce on these lines the support condition. So this rigid line support have to be reduced. What means now that these cables, what we have, will bring in its end force to this arcs. So this side and this side is fixed, but these front nodes are quite flexible and should be still fixed. So we select it and add here a support, for example, here a hinged support. So so far everything is clear, but when we take now a look on this member type cable, these lines will be removed and maybe hide the rest. You will see that this cable is now the boundary, but for the program the question appears which condition I should use. Should I use exactly this stiffness of cable, or have the cable a specific pre-stress? Is there some starting condition? And yes, you can define it here in this load case for the form finding, and open here maybe member load and define here form finding, and for example say here you can say a force, maybe average force, or for example a sag. And here we say, okay, we want to have 1 meter sag. So now let's bring up this sag on these cables. It looks like a member load, and if we run this form finding task again, the program search a shape of membrane which holds this pre-stress what we defined, and also takes care that these cables have a sag in spatial direction with 1 meter. This ends up in a, let's say, tension force of almost 30 kilonewton. It's not constant. And if we take a look on shape itself, you will see that maybe from top view that we have now a sag inside the structure. And if you take a look in this direction, even the sag is going in direction to the membrane. So far, it's nice. And even if you turn on results, you will see that even this supports overtakes now or gives you some forces. And if you see everything, yeah, the membrane is hanging on these cables and giving forces to arcs and to these supports. So far, we have now defined a shape consisting on these 2 arc pairs, and we are now in the situation to start with our regular structural analysis job. What means we have to check if the structure can consist snow load, self weight, wind loads, and so on. And for this, we have to define load cases. I start with our first principal load case. I open here this load case and combinations menu and specify here a new load case, for example, self weight. And yeah, it's a static analysis. It should be done according large deformation theory because it contains cables and membranes. And the action category is, of course, permanent. And now, of course, you can use OK, but there is a question, because the program have now to know if you run load case 2, what should happen? Should it use the shape from load case 1, or should it start from initial mesh geometry without pre-stress? And this question you can answer with the initial state. So you can say here load case 2 should work with the initial state, and here you can specify, for example, the shape what we just created in load case 1, what was suitable or what was okay, and you overtake here the final state, what means the moved mesh geometry and the internal forces. And if you run this, you get now an analysis according the previous done shape in load case 1. And if we take a look, you can check it quite easily. Here we can, of course, activate results, but if you take a look here on pre-stress, you see, oh, I forgot something. Yeah, you see this is 0 load in C, and the same for surf weight, because we have no forces in this load case. We need, we have to activate something. We have to activate the surf weight. And now let's run it again. And now let's hope that this sum in C have this contains these forces. And now load case 2 have these forces and load case 1 not. So this is maybe good for plausibility check. In the next point, we can add maybe further load cases. What should happen? For example, snow. And here we change the category to snow, and we can add, for example, the different load schemes what are appearing according standard, but let's use the easiest one, maybe projected load with 0.252 and bring it up on these surfaces. Yes. So this is maybe one easy load case to define. The next is more complex, because when we want to create the next would be, for example, wind load. And as mentioned in introduction, this shape don't match any scheme from any code. I can recommend to do it with a digital wind tunnel test. And here we offer a wind simulation with Rwind. And this you can maybe do with the help of Rfem and Rwind by defining here right load cases. But if you place this model into a wind tunnel, you have to know that the wind can maybe press here again, but it can also flow downwards and upwards. And this is not real, because here we have a building on below. So if you do wind tunnel analysis, you have to give the program a model what fits to this. And therefore we have to model also these walls inside. And for this, we go back to our starting line risk. What means we select here this initial line part, yeah, and use these lines to model the wall of the remaining structure. So select all these lines here. No. Okay, now we can copy this stuff by create a copy with a displacement vector. And here, I don't know how high this building is, but we can use our background layer and create here between the origin lines and copied lines a new surface. And because we don't want to model now the full building, I simulate it as rigid. Yeah, this is the easiest one. And yeah, we store it. And now if you visualize it, we have these walls inside. And of course, because it's a finite element program, we have to fix it against deflection. So they need a support. Yeah. So yeah, let's place here a line support below. It's here type for lines. But if you see this, the question could appear, can't we connect the membrane directly to the walls? And yes, we can, and I would do it also. So let's remove these nodal supports here. Nodal support, delete assignment, and fix these nodes of membrane edge to these walls with, for example, a rigid arm. And this rigid arm is only a symbol for any secondary load-bearing structure. Whatever what you have to model here, it only transports these forces from the cables to let's say the wall structure, and move it or produce it or transform it down to the line supports what we just defined. And I define here with this rigid member only a connection between these two nodes. Now, so far, the structure is ready for a wind tunnel test. Yeah. The wind can press here, can have suction on the back, but maybe we have one lag here. The wind can blow inside the structure, and I assume it will be closed in reality. So here you can give our meshing tool a hint, how to say, in wind simulation, please close openings smaller than the real size, for example here 2.3 meters, and keep results if the mesh in Rfem is deleted. And with this setting, the program will also close this gap here. Yeah? So now we have to set up the wind analysis definition, and this will be done with, in this case, with the load wizard wind simulations. And in wind simulations, you can define the calculation parameters, with steady flow, properties of medium, iterations, final residue, and so on. And the wind profile, what is finally the load for this calculation, which wind speed we define on entry of the wind tunnel. And here we say, we know it's in Cologne, so let's take over. The information may be here from the musical dome. The program will find it, and you see, maybe let's check the situation exactly. It's near the central station. Here was the exhibition, and we saw it when we drove with the train over the Rhine. And we have here a basic wind speed of 22.5 and the resulting pressure. And this data we can overtake. And the program not only overtakes the wind speed and pressures, and also the address, geocoordinates, zone data, and gives us this wind speed diagram. And you can also say, okay, you want to have maybe a constant turbulence intensity over high. So this is turbulence intensity, this is wind speed, and this is our entry for the wind tunnel test. And finally, to close it up, we have to say from which directions the wind is coming. At the moment, we have an increment of 10, but we can also write here, for example, 90 degrees, what means we get here maybe wind in 0, 90, 180, 270. And if you say, I don't need this 270 solution, you can change here to user defined and delete these 270 solutions out of the range, and you get only here 3 load cases. And after confirmation, you get here 3 wind load cases with these respective wind tunnels around. So maybe take a top view, you see how the wind tunnel is going around this structure. So now we have defined all our load cases, and we can sum it up in a combination. For this, I go into this load case and combinations menu again, where I specify the wind wizard, or a combination wizard, sorry, for the standard, what is selected here, and specifying design situations, which design situations I want to check for my design add-ons. So stress strain and steel should be done, for example, only this ULS. The SLS I remove because this presentation, I think for explaining it's enough. And now you see, okay, this design situation is activated for this design add-ons. And now we have to define in the wizard settings how this combination should look like. We can say it should be done according large deformations, according Newton-Raphson solver. Imperfections are not needed, and because we don't know it right now. And the initial state, please use for all this pre-stress in or shape from log case 1. And this ends up in following load combinations where the program is combining all forces with all its others. And now we set up the model with load cases and combinations, and we should calculate all. The case is only I don't want to wait now, therefore I prepared here a finished analysis, what is already calculated, and you see we have already results here, even for these wind load cases. And if we take a look what happened here when we press calculate, the program is giving us here for these wind load cases, for example, let's take this 90-degree edit. It's a two-staged analysis. What means at first it do a wind simulation in the wind tunnel. What you can see here in our wind, you see, okay, this is wind against this length or according this building site. Here you have a picture of this wind tunnel, what is considered. And finally, this ends up in, let's say, start with the another result domain. So we detect here the pressure around building. You see we have positive and here negative pressure around. Even for velocity, you see this is the result around the building. We know, or we simulate exactly on the places which wind speed is here, and also beside pressure and wind speed, the wind direction. And if you take here maybe a look in vertical, you see how the wind is maybe here moved around the building, what gives you finally even the information of the wind flow, where you see, okay, the wind is flowing around the structure in this manner. Of course, you can animate it and can produce for your client such pictures or animations. And for us, what is important here is that we can detect from the pressure skin around a pressure on the building, where you see, okay, we are here maybe in positive pressure, and here it ends up in a suction. And these forces are overtaken to Rfem. And gives here, let's say, deflections and forces on the structure. You see now here how the membrane is pressed in, and even forces for the members which can be used for design. And if you finally combine all these forces, you get a design situation for design, which sums up everything. And if I take here a closer look on the normal axis forces, you see, okay, after using all these combinations, we get here a really ruling compression force in the members. And if you want to know where to find, you can go here to maybe table static analysis, results by member, and if you turn on here this design situation, you see, okay, this governing normal axis force, this negative one, is coming from CO8. No? Let's see what is CO8. CO8 is, if you open it, CO8 is here, and it contains pre-stressed self-weight snow. So it's not a secret. I think we could detect it also by ourselves, because it's clear snow is giving the biggest pressure in these arcs. But you see how it meets each other. And now to the question stability. If you don't know if this is now a crucial situation or not, you can activate here even the calculation of critical load with, for example, here using 100, calculating 100 lowest eigenvalues with the eigenvalue method. And if you calculate this stuff, you will get, besides the static analysis of the CO8, also a stability analysis. And you see here, the lowest factor is here 2.3 with an increase of 1.7, what is quite critical. But if we take a look only on members, so members without surfaces, yeah, let's use this without figures. And take a look at top view, you will see that the member will buckle here out of plane. Maybe use here also deformation section colored, and it's more clear. You see this is only a buckling of these truss members out of plane, but no global deflection of the structure. So it's only these eigenvalues of these truss members. Yeah. Maybe you see it here much more better if I go into the isometric view. And at any point when we go through these eigenvalues, maybe I think nearly here, where it is, here you see now even this whole curved beam, this arc will buckle. If we see here, okay, with the eigenvalue of 20.07 with an increase of 5%, we have also a buckling shape of the main beam. And because it will not increase the results by more than 10%, I don't see it so critical, even with knowing that we already calculating geometrical nonlinear with wind loads. So I don't see this as critical stability issue. The points with this buckling of these truss beams is governing, but here I would say we have to design it with a buckling check. So I select all these truss beams with this 250 diameter cross section and say here members, edit, and go here to design types and add here a buckling length or a buckling check. Because it's a closed cross section, we can remove torsional buckling and only do buckling check about Y and Z axis for a fixed start and end situation. And if we run here the steel design now, you will see that the cross section check and stability check will be done for these elements. Maybe display all beams. You see some elements are green, others not, but generally maybe take here design ratio on members. You see, okay, for all, for example, let's take out one element here. This beam is okay for the section proof, all green, only the stability check is red. And if you are interested why, you open the details and take a look on the sum up. Maybe let's scroll down the hand calculation, and you see maybe the final utilization is done by these separated terms. The normal axis force term almost eats up the potential of the beam plus bending. You are overutilized, so let's increase this cross section. If you want to do also the design for these surfaces, we added in begin this stress strain analysis. Here, let's say members we don't have to design because it's done from steel design. Let's design only the surfaces. And because we know these membranes have maybe warp and weft stiffnesses or strengths, we should learn the program to do it in this manner. The program allows us to check every stress component manually, maybe meso stress, principal stress, but this is uninteresting here. In our case, we need only maybe a check in X and Y for WOP and WEF direction. And because we don't know limit normal stress, you can specify it here with a user-defined input. So you can detect from your by-Excel test what you get from your manufacturer, the finite test strength. And here, for example, let's use 30 MPa and maybe 26 MPa for the WEF direction. And you see how it's calculated with this formulation here. And after confirmation and calculation of the stress check, you will get also this information as colored picture. Let's activate everything, and you see here this is maybe the stress distribution for the X direction, for the Y direction, and this is maybe existing stress, and compared to limit stress, you get it also in the same manner for X and Y, and you see here as multicolored plot what is red, what is overutilized and not overutilized. And this brings me now to the end of my presentation, and I give back to Andreas.
Okay, thank you, Andreas, for this nice presentation. Although I already shared the link in the chat where you can find the recording, I would like to show it on our website. It takes only a few minutes, just a moment. On our website, dlubal.com, you can find under News and Events the webinars. Then you have to scroll a little bit down and then click on today's webinar, and you will find the recording the next days here. Also the model, that's the finished model, yeah. And you can use the program, or if you don't have the program, you can use the full trial version here at the top of the page. I click on it, and then you can download Rfem 6 and with all add-ons, wind, and you can try for yourself, for example, with today's model and so on. Yeah, that brings me on to the end of the webinar. I would like to say thank you for your attention. Thanks to Andreas Niemeyer for this nice presentation. Thanks to Stefan Hoffmann for your help in answering the questions. I wish all a nice rest of the day. Maybe a last information, there's a small survey when you leave the webinar. You can score us and answer some questions, or you can skip the question by a line or so. Just note that the worst score is 1 and the best score is 5. It would be very nice. It will take only 1 minute, I think. Okay, then bye-bye.